Hello and welcome to another wonderful day of physical chemistry. So today we're going to be continuing our conversation of thermodynamics by looking at the expansion and compression of a system and how this is going to be related to the amount of energy moving in and out. So as we've established previously, when we're looking at thermodynamics, what we really want to monitor is the flow of energy. Now, it turns out that for most systems, this can be a bit messy. So we're going to want to start with a simple of a model as we can, and then we can slowly add complexity to it. So it turns out that one of the simplest models I can make use of is essentially going to be a piston, which we can think of um, as a metal cylinder where I can go ahead and apply force to the top of the cylinder, allowing compression or expansion uh, of the cylinder, essentially in turns. And we can relate this compression and expansion to the change of internal energy with the equation we derived last time from the first law of thermodynamics, where any change of internal energy of the system itself is going to be related to the amount of heat flowing in or out of the system, plus essentially the amount of work either performed by the uh, force applied to the top of the container, or uh, alternatively, the amount of force applied to expand the container. However, we often need to look at the system not just in terms of these kind of discrete changes of internal energy, heat, and work, but also in terms of how much the internal energy is changing at any given moment and the corresponding momentary heat and work. And it turns out we can do this by moving to an infinitesimal form. Now, it turns out that, as we've seen previously, descriptions of the internal energy get a little bit messy as there's a lot of various ways the internal energy can change. Similarly, heat itself can also be a little bit tricky. So a good starting point to try and describe our piston is going to be looking at this work component, because it turns out that we can use a lot of the principles we've built up in physics to describe this system. However, I want to try and make this applied work be as simple as possible. And one of the best ways to do this is by making sure that that the force applied to the top of my container is more or less constant. And we can apply essentially a constant force by using a weight of fixed mass to go ahead and compress the system. Because as you know, if I take a box, I throw a weight on top of it, we would indeed expect it to go ahead and compress, which means I'm finding some way to input energy into my system. So let's go ahead and break this down with some of our physics principles. So as we've seen previously, the amount of work applied to a system is going to be related to the potential energy, because the potential energy can be thought of as the maximum amount of work that can be obtained from moving the system. So in turn, we can relate the change in potential energy of a weight based on the amount of force it takes to move this weight times essentially the distance I moved it. So what we can then do is use some of our principles from physics to know that our force is going to be related to mass times acceleration, which for a weight is going to also be the same as mass times our gravitational acceleration, or our gravitational constant. So if you need to determine the force applied by a fixed mass, this is going to be your go-to equation. However, as chemists, we often don't like working with size-extensive properties like mass, and instead like to work with size-intensive properties like pressure. So what we can do is use another set of equations to relate force to the pressure being applied to the top of our container times essentially the area of the top of our container. So once we have this equation for a force in terms of pressure and area, we can insert this back into our momentary work equation, which gives us the amount of work being done at a given time being related to the pressure that the weight is applying times the area of the top of our container, or the amount of area that pressure is being applied over. And similarly, the more that we compress the system, the more work needs to be accomplished. So it's not too surprising. We're going to see a relationship in between the amount of work performed and the amount of compression obtained. However, it turns out that we can simplify this system a little bit more by realizing that the area of the top of the container times the amount of distance that I'm displacing the system is going to be the same thing as the change in volume. As the greater the amount of compression, the greater the amount of volume I've removed from the container. So this gives us an expression for the amount of work in terms of the pressure applied and the amount of volume removed from the system, or the change in volume of the system. However, turns out that we don't always want to work in a momentary basis. So in order to obtain the absolute amount of work accomplished by tossing my weight on top of the system, I'm going to want to go ahead and integrate over my initial volume to my final volume, or essentially the amount of distance the system has been compressed or expanded. Now, one of the reasons why using a weight of fixed mass to compress our system is quite useful is that it turns out that since the mass of my system isn't changing, and also turns out that the gravitational constant shouldn't be changing, one hopes, that what we end up having is the amount of force and thus pressure being applied to our system is going to be relatively constant. So this gives us what's called an isobaric compression, because we have a constant external pressure. And because our pressure doesn't depend on volume, it means we can pull out a negative p term out in front of our integral. So then our integral simply becomes the integral of dv, which gives us delta v. So what we now have is an expression for the amount of work being related to the negative of the pressure being applied to the system times the change in volume of our piston. And one of the things that's really cool is because of how we constructed these equations, it doesn't matter whether we're talking about a compression or an expansion. These equations will hold regardless, where I can always get the amount of work from a compression, isobaric compression or expansion, as long as I know the amount of pressure being applied and the change in volume. And one of the things it's always worth taking a look at after you've derived equation is to make sure that all of the signs work. So in this equation, we know that our pressure should always be positive. As it turns out, it's very hard to get a negative pressure. And if I'm compressing the system, the amount of volume in my piston should be decreasing, and I should have a negative delta V. Now, this negative sign on the delta V will cancel out with the negative sign out front, and this gives us a positive work value, which should hopefully make sense, because if I throw a weight on top of my piston, I'm essentially putting energy into my system, which gives me a positive work value. So again, our signs do end up holding. And it turns out that this is going to be a fairly useful equation for us to make use of anytime the pressure being applied to a system is relatively constant, which may be more often than you'd think. However, one of the things that's also worth examining is, let's say I go ahead and I throw my weight on top of my piston, the system then compresses. Then what we want to try and want to figure out is what the change in energy would be if I go ahead and remove this mass from the system and allow my piston to essentially return to where it started. So let's go ahead and think about how much work the system uh, requires for the gas to expand back to its original position if I remove the weight. So it turns out that we can use our same general equation, where the work that this will take is going to be related to the integral of the external pressure times the change in volume. However, let's go ahead and make an approximation here and assume that the atmospheric contribution out here is fairly minimal and I have no opposing force. So if I have no opposing force or pressure resisting this expansion, my external pressure is zero, which means I'm then taking the integral of zero. Well, it turns out that that gives me a work of zero. So this ends up being called a free expansion. So if my system is expanding against no external force, my system does no work. And this should make sense based on our original definition of work, that work is essentially the amount of energy it takes to move a system against an opposing force. Thus, if I don't have any opposing force, as we have in cases where we have no external pressure, we do no work. So this actually brings us to an interesting point, which is the fact that work is what we call a path function. In that when I applied, I have the same initial and final point. When if I throw my mass on top of my piston, I compress it, I put work in, but when I remove the mass, I essentially get no work out. So essentially, this whole process, despite the fact I returned to where I originally started, we have a network into the system. And this is an important thing to keep in mind as we go on, that that work is very much going to depend upon the path that we take. So let's go ahead and look at maybe a more complicated system of, let's go ahead and say that I want to go ahead and compress or expand my system again. So let's go ahead and say that I now removed my weight, but I acknowledge the fact that I may have some opposing pressure. But this opposing pressure actually can change. Well, then we get into a little bit of a tricky bit. Because if I'm trying to integrate this equation, and pressure is not going to be constant with the position of the system, it turns out that my external pressure will depend upon the volume of my system, which means I can't pull out my external pressure from the integration. And that means I can't solve this problem unless I know something about how the external pressure changes. So if I'm going to try and solve this problem, I need to know something about how my external pressure changes. And it turns out one of the simplest cases would be imagining if my external pressure and the pressure inside my system are in equilibrium. So that would essentially be a way of saying that my opposing pressure is going to be the same as the pressure inside my system. And I might be able to say measure the pressure inside my system with something simple like a barometer. However, it turns out that this case has a special name. This is essentially called a reversible conditions if my external and system pressures are in equilibrium. So one of the things that we should take into account is, let's say I'm trying to expand my system with these two pressures in equilibrium. How long would it take to actually expand the system under these conditions? Well, if my two pressures are perfectly opposed, then it turns out I won't see any change. Thus, the system and the surroundings are in equilibrium, which means that if I allow these two pressures to be perfectly matched forever, it will take literally forever for any expansion to occur, because there's no force or pressure from the system causing this border to move. So this actually becomes a slightly problematic scenario, as it turns out that we will never truly have reversible conditions. However, one can imagine that if I allow my system pressure to be ever so slightly larger than my external pressure, I would slowly see an expansion of the system. So most of the times in practice, when we're talking about a reversible expansion or a reversible process, this is another way of saying a process that we allowed to take a sufficiently large amount of time that any change occurred very incrementally. So a good way to think about reversible conditions is it's never something you quite achieve, but it's something that you can approach quite closely. And this is one of the reasons why, to get good results in a lot of our chemistry labs, we try and take a sufficiently long time for things to come to equilibrium to essentially try and ensure reversible conditions. However, it turns out that under these conditions, what I can do is replace my external pressure term in my work equation with my internal pressure term. So this is one of the things that I'm going to try and be very cautious about when I use these equations. That when I use pressure without a subscript, I'm going to be referring almost exclusively to the pressure of the system. However, it is worth noting that a lot of books and other resources will slip up and occasionally give an unsubscripted pressure term to refer to the external pressure. And it turns out that these two phenomena are actually quite different. And one of the most powerful features of reversible conditions is allowing them to be treated simultaneously. So let's say that I now have this reversible equation. It turns out that unless I have a good way to get this pressure term, it can still be a little bit hard to predict the behavior of this expansion and resultantly the work equation. However, let's assume that the gas inside my piston is fairly well behaved. Then it turns out that I can go ahead and use the ideal gas equation to replace my pressure term with nRT over V. So when we go ahead and do this, what we find is that it's going to be possible to remove the amount of substance term from the equation, because this will not change. And we can also remove the gas constant because it's a constant. So both of these can pull out front. Then we actually need to make an additional approximation. At this point, we need to assume that temperature is also going to be constant for this expansion. Thus, we're going to be treating an isothermal reversible expansion. So we're making two separate approximations. So if we do this, we can pull out our nRT in front of our integration, and then simply take the integral of dV over V. Now, turns out that this gives us one of my personal favorite integrals, with a resulting value of natural log of V. However, since we're working under limited conditions of V1 to V2, this is going to give me the difference of the natural logs of the volumes, or ln of V2 minus ln of V1. However, it's possible to write the difference of natural logs as the ratio of the final and initial conditions. And so you'll often see the work for an isothermal reversible expansion generated in this equational form. And it turns out that this equational form will hold for both, again, expansions and compressions, because we are not specifying whether V2 or V1 should be larger. But again, let's assume that we're working with an expansion condition, at which point the system should be performing work and will have a negative value for work. Now, if that happens, N, R, and T should all be positive values, and V2 should be greater than V1. So the natural log of that ratio should be greater than 1. So this ratio should be greater than 1. So the natural log of this ratio should be positive. So positive, 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 whole term ends up being negative due to this prefactor. So this is, again, a way of confirming that an expansion should end up generating performing work, and a compression requires work. Now let's go ahead and try and compare our isothermal reversible expansion to our old friend, the isobaric reversible expansion. So the simplest case might be something like an isobaric expansion, where I have an initial pressure of Pi, and I'm expanding against some lesser force, say 1 atm, and my system will slowly increase in volume until my internal pressure reaches that final value of 1 atm. So in this case, we can model the amount of work done by the system in the expansion based entirely on that ending external pressure, so 1 atm, times the amount of volume the system expanded. So this is actually going to be a fairly simple approach. However, what we can do is compare this to the reversible expansion, where in this case, my expansion is going to occur much more slowly. And so originally, say I start with an internal pressure of 2 atm. Well, my external pressure is going to also be 2 atm. And then I'm going to slowly remove pressure, allowing my system to slowly push my piston up as I slowly remove this pressure. And this whole time, my internal and external pressure will be identical and can be given by essentially nRT and the ratio of the volume. Now, what ends up happening is when we plug this into a reversible expansion equation, it turns out that the amount of work we get out of the reversible expansion will always be greater than the irreversible expansion. And one of the ways you can think about it is that as I have a greater applied pressure, say from my piston, I'm doing more work to move that piston. Now, when this might become really important is, let's say that I'm trying to use compressed gases inside a piston to essentially drive a flywheel. Well, if I just unhook the piston quickly, then my system will quickly expand, but I'm not going to be driving my wheel at all. However, if I allow the system to essentially slowly expand, this will give me extra energy, which is going to go into moving that wheel. So this is, again, some of the same ideas that we saw for free expansion versus isobaric expansion. And one of the good take-home points this tells us about chemical processes is that in general, you can get more work out of a system by taking it low and slow. So hopefully this gives you an idea of how we can describe the work out of several simple chemical systems, again, just by looking at the behavior of the expansion and compression of a gas phase system. So next time, we're going to be taking a little bit more time to look at the behavior of the heat of the system and how this might relate to the net internal energy. Until then, take care.